Hello and welcome. My name is Victor Gijsbers and I teach philosophy at Leiden University in the Netherlands. In this video I want to talk about a 2019 article by Anat Schechtman. This article is called 3 Infinities in Early Modern Philosophy, and it is about the concept of infinity in basically 17th century European philosophy. And what Schechtman is going to do, she is going to talk about 3 philosophers, 3 of the main philosophers of the period. She's going to talk about Locke, Descartes and Leibniz. And her argument is that these 3 philosophers mean something different with the notion of infinity. Now, as far as I can see, the 3 notions of infinity that we get here in early modern philosophy have precursors and they have successors. I mean, these are not ways of thinking about infinity that appear from nowhere or that disappear without trace. These 3 philosophers are clearly within a long tradition that is continuing until today in the philosophy of infinity. But I think it's useful and interesting to see how this thinking about infinity plays out in the 17th century. So let us follow Schechtman. And what Schechtman will do is she will first look at Locke, then at Descartes, who is in a sense the outlier, I would say, among the 3, with the most different conception of infinity, and then at Leibniz, whose view is closer to Locke, but still different. So, Locke. When Locke thinks about infinity, he is thinking about infinity as something that is quantitative. And we will see that Leibniz agrees with that and that Descartes disagrees with that. But for Locke, infinity is a quantitative term. So what is infinite? Well, the numbers, for instance, the natural numbers are clearly infinite, right? There's 1, 2, 3, 4, 5, 6, 7. How many of those numbers are there? Well, there's not 1,000 of them. There's not 1,000,000 of them. There are infinitely many of them. So that's one thing that's infinite, right? And it's clearly a quantitative measure. It means that there are a lot of numbers. Maybe space is infinite, right? Space is definitely large. We can see fairly far into it, but maybe it's not just large, maybe it is infinite. According to Schechtman, when Locke explains what infinity is, his central idea is that infinity has something to do with quantity, and then that quantity has something to do with measurement and measure. Now, when we think about measuring, what we're thinking of, at least in the way that Locke is presenting this, what we are thinking of is a procedure that works something like this. You take some kind of unit, and then you count how many of those units are in the thing that you want to measure. So, for instance, if somebody asks me how long a week is, what I need to do is I need to take some kind of unit of time, for instance, a day. And then I can count how many days there are in a week, and the answer is 7. And of course I didn't have to take a day, I could also have taken an hour. And if I'd taken an hour, then there would have been 7 times 24, which is 168 if I'm not mistaken. There are 168 hours in a week, and that's also fine. I mean, it's basically, it comes to the same thing. But that's the idea that is the idea of measurement, right? You have this unit and you apply it again and again and again until you have filled up the thing of which you want to take the measure. And so, and I'm quoting from Schechtman's article now at page 1123, something is a quantity just in case it is divisible into unit length parts that can be numbered or counted. So something is a quantity just in case it is divisible into unit length parts that can be counted or numbered. Well, that works really well, of course, for finite things, but what about infinite things? Right? I can do 1, 2, 3, 4, 5, 6, 7, and I have numbered all the days of the week. But how do I number all the days of eternity, of an infinite time? You know, you can't do that. That's right, says Schechtman, but there are 2 ways in which we can think about counting. Right? One way is what she calls enumeration, which is just going 1, 2, 3, 4, 5, 6, and so on. And that doesn't really work for infinity because you're never going to get to the end of that. The other she calls tallying. And tallying has to do with taking 2 sets of things and putting them 1-to-1 together. Right? So here's a way to find out that there are 7 days in a week. You take the numbers 1 to 7, and you take Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and you put a number next to each day, and it turns out that there are just as many numbers as days, in the sense that you don't have any numbers left over, and you don't have any days left over. Right? If you have these 7 numbers and these 7 days, and you put them one by one together, every number has a day, every day has a number, there's no numbers left over, there's no days left over. That's when we say, okay, yeah, there are equally many numbers here as days. Now this idea of tallying, this idea, to say it a little bit more in the vocabulary of contemporary mathematics, this idea of a 1-to-1 correspondence, so having things like correspond 1-to-1 to each other, this idea of counting does work for infinite things, right? Because now what I can do is I can say, oh, well, let's take eternity, right? And let's break eternity up into years. Well, the years that I have when I break up eternity into years can be put into this 1-to-1 correspondence with the natural numbers. Right? There's a year 1, a year 2, a year 3, a year 4, a year 5, a year 6, and so on. And for every number there's a year, and for every year there's a number. There's equally many of them. So that's a way to think about infinity. And Schechtman says this is one of the 2 sort of central thoughts about infinity that shape Locke's thinking. And here's how she phrases it. She says, a quantity is infinite just in case there is a pairing without remainder, so a 1-to-1 correspondence, between its unit parts and the natural numbers. So a quantity is infinite if you can pair it without remainder with the natural numbers. So no numbers left over, no unit parts left over. That's what an infinite quantity is. Well, that sounds good. There's actually also another way of thinking about infinity that you find in Locke, but they fit together like perfectly. And this other way of thinking about infinity is the following. Right? If you have an infinite quantity, then however big a finite part you think of, it's gonna fit within that. Okay, so let me explain that again. Suppose you think of eternity. Now, think of any finite length of time. 1,000,000 years maybe. 1,000,000,000 years. 1,000,000,000,000 years. It's always going to fit. Right? There's always going to be a part of the infinite thing, in this case a part of eternity, that is that big. Right? There's going to be a part of eternity that's 1,000,000 years. There's going to be a part that is 1,000,000,000 years. There's going to be a part that is 1,000,000,000,000 years. No matter how big the finite part is that you come up with, it's going to fit into this infinite thing. And so that gives us a second quantitative condition. And again, I'm quoting Schechtman. A quantity is infinite just in case it has arbitrarily large finite parts. Now, these 2 conditions are not in competition. They're basically 2 sides of the same coin. Right? The ability of being put into 1-to-1 correspondence with the natural numbers, and the fact that you have arbitrarily large finite parts are 2 sides of the same coin. They belong together. They are both, one could say, necessary and sufficient for something to be an infinite quantity in Locke's sense of the term. Okay, so that's Locke. And in thinking this way, Locke is quite close to modern mathematics. There's one difference, which is that Locke does not posit the existence of infinite numbers. When modern mathematics posits the existence of posits the existence of infinite numbers. Numbers that have like these beautiful names. I don't know whether they're beautiful, but names like Aleph 0 and Aleph 1 and so on. I mean, there's a lot of infinite numbers posited by modern mathematics. Locke is not doing that. I mean, that's not going to happen until fairly late in the 19th century. But otherwise, his way of thinking about quantity as this 1-to-1 correspondence, his way of thinking about infinity as quantity, that fits contemporary mathematical thinking about the infinite very well. So let's move on to our second thinker. And our second thinker is Descartes. And Descartes really doesn't like the idea of infinity as something that is very big, as something that goes on and on and on. And in fact, Descartes refuses to use the word infinite, for instance, about the natural numbers. He says, no, I don't want to call that infinite. I'm going to call that the indefinite. Right? You can't really measure it. It's sort of, there's something wrong with it. It's never complete. Well, that's not how Descartes wants to think about infinity. For Descartes, infinity is precisely that which is complete, that is, which is self-sufficient, which doesn't require anything else. Right? To be infinite is to be independent, self-sufficient, existing sort of on your own without needing anything else. And for Descartes, what this means is that the idea of infinity, first of all, belongs primarily with the idea of God and also with the idea of being. Right? To be, to exist, is in the first instance to be an infinite substance that exists in itself without requiring anything else, without any dependence. And of course, this infinite substance that just is identified by Descartes as God. And everything else, right, everything that is not God, is in a sense a lesser being, because it is a being that is dependent on something else. Right? We are dependent on God. We are dependent on God because God created the universe, I suppose, but we are more dependent on God than that, according to Descartes. Right? God sustains our being at every moment. If God didn't do that, we wouldn't exist. We have no power of existence, not just of coming into being, but even of just continuing to exist, or I suppose even of just existing without God. Right? And so the infinite for Descartes is basically being with a big B, like being itself, being independently. It is God. It has nothing to do with quantity. Right? God is not big. You can't say that God is big. I mean, that is to completely misunderstand what this conception of the divine or this conception of being is. God is not like really big. God is not the biggest number or something like that, or the biggest space or the biggest time. God is infinite in a completely different way. And Schechtman calls this ontic infinity, an ontic conception of the infinite, where ontic means that it has to do with being. Right? And that makes perfect sense. So, to quote her, Descartes views infinity as the highest or unqualified degree of being, where the latter is equivalent to absolute independence. And then she defines the ontic condition of infinity in the following way. A being is infinite just in case it has the highest degree of reality, where something has the highest degree of reality just in case it is absolutely independent. Okay, so Locke isn't claiming that space is independent or that the numbers are independent. He's talking about something else, right? He's talking about what Descartes calls the indefinite. Descartes says, no, look, the infinite, it's God, it's independence, it's being. All right, let us move on to the third author. And the third author is Leibniz. Now, before getting into Leibniz, Schechtman presents Galileo's paradox. And this is a very well-known paradox about infinity. And it goes like this, or it goes like this in the way that Schechtman reconstructs it, which I think is a very useful reconstruction. So I'm actually just going to read that out. This is page 1136. And by the way, this 1100 something, it's not that Schechtman wrote an insanely thick book. It's just a journal that numbers the articles consecutively. So there are just a lot of articles, and then at a certain point you have articles that have very high page numbers. Okay, so here is the reconstruction of Galileo's paradox. 1. The squares of natural numbers are a proper part of the natural numbers. So what does that mean? Well, if you have the natural numbers 1, 2, 3, 4, 5, 6, and so on, and now you think about the squares, right? What are the squares? Well, there's 1, there's 4, There's 9, there's 16, there's 25, and so on. Right? Those are the squares. Those are a proper part of the natural numbers. All the squares are natural numbers, but not all the natural numbers are squares. So some of the natural numbers are squares, but not all of them. That's what this means. So, okay, so that's 1, right? Idea 1, the squares of natural numbers are a proper part of the natural numbers. Idea 2 is something called Euclid's axiom. Euclid, an ancient Greek geometer. Here's the axiom. A whole is greater than any of its proper parts. Right, then again, a proper part is a part that is not the entire whole. So a whole is greater than any of its proper parts. Well, that seems to be right. Okay, so take my Nietzsche bust. One of its proper parts is its mustache. Right? Every Nietzsche bust, of course, has an impressive mustache. So the mustache is a proper part of the Nietzsche bust. Well, the whole of the bust is greater than this proper part. And that would be true for any proper part. Right? So Euclid's axiom sounds pretty convincing. A whole is always greater than any of its proper parts. Those two ideas together obviously imply that the natural numbers are greater than the squares of the natural numbers. Right? There are more natural numbers than squares of the natural numbers. This follows immediately. Okay, idea 3. There is a pairing without remainder of the squares of the natural numbers with the natural numbers. Right? So we remember this idea of pairing, which was Locke's idea of being equally big, equally many. And we can do that with the natural numbers and the squares. It's very easy. You just pair each natural number with the square that belongs to it. 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, and so on. Are you going to have any natural numbers left at the end? No. Every natural number has a square. So this pairing just works. Every square gets a number. Every number gets a square. There is no remainder. Okay. So that's important, right? The natural numbers and the squares, you can pair them with no remainder. And so if we accept idea number 4, this pairing principle, that when you can pair off two sets, they are equally big, then it follows that there are just as many natural numbers as squares. And now we have a problem, because the first two ideas, right, using Euclid's axiom, prove that there are more natural numbers than squares. But idea 3 and 4, which include this pairing principle, show that there are just as many natural numbers as squares. And so we get the rather unfortunate conclusion that there are more natural numbers than squares, and there are just as many natural numbers as squares. And that's a place where we don't want to go. So what do we need to do? Modern mathematics tells us to ditch Euclid's axiom. Right? Modern mathematics tells us to just accept the pairing principle and to ditch the idea that a whole is always greater than any of its proper parts. That is supposedly true for finite things, but not for infinite things. Right? The natural numbers just are not bigger, not more than the squares. And that's possible. And that fits basically what Locke was supposed to be doing. It's not what Leibniz does. Leibniz considers this paradox, and what he tells us is that there is another way out. He doesn't want to give up on Euclid's axiom. Right? He wants to keep the idea that a whole is greater than any of its proper parts. But he also wants to keep the idea that the natural numbers and the squares are, equally great. That this pairing principle is a good principle. So how can you do that? Well, there's one way to keep both of those axioms without getting into a contradiction, and it's this. You deny that in the case of infinities, there is a whole. Right? If there's no whole, if the natural numbers are no whole, then, maybe a whole is always greater than its proper parts, but there's no whole here. Right? There is no set of all the natural numbers. And if there's no whole, then you can't even apply Euclid's principle and you don't get into a contradiction. So what does that mean, to deny that there is a kind of, well, to deny that these infinite sets are wholes? Well, actually, it's a move that we, I suppose, already see in Aristotle when he comes up with the idea of a potential infinity. Right? So for Aristotle, I mean, Aristotle is, among other things, considering Zeno's paradox, where you take a length, let's say a racetrack, and you divide it up into smaller and smaller parts. And what Aristotle says is, well, you can always divide it up more, but you never get to the point where you have divided it up infinitely many times, and you have all these infinitely many, infinitely small points. But you don't get there. That's not something that exists. And so Aristotle basically seems to be arguing that there is no such thing as this sort of achieved infinity. Well, that's the kind of thing that Leibniz can be saying here too. Right? Let's think about the numbers. He can say, look, the numbers are such that you can always keep on counting. So there's an iterative conception. This is Schechtman's term, an iterative conception of infinity. You can always go on, 1, 2, 3, 4, 5. It's never going to stop. But there's no hole there. Right? There's no such thing as all the natural numbers. Okay. So if you want to work that through logically, if you want to think about how to formulate that in a sort of perspicuous way when you talk about numbers, one way to do that is this, right? You could say that Leibniz agrees that for every natural number, there's another number that's bigger than it. So for every natural number, there's another number that's bigger than it. 1 trillion, well, 2 trillion, right? Whatever number you say, I can come up with a bigger number. But it's not the case that there is a number that is bigger than all the natural numbers, right? There's no such thing as the number of numbers or the number of natural numbers, right? That doesn't exist. Modern mathematicians have no problem sort of positing that. They call it Aleph zero. But Leibniz, with this iterative conception of infinity, doesn't want to do that. At the end of the article, Schechtman returns to this idea of measure. And she says, well, look, what seems to be the sort of main distinction then between Locke and Leibniz is that Locke does and Leibniz does not accept the idea that there is such a thing as infinite measure. Right? For Locke, there is a measure which is bigger than all the finite numbers. And for Leibniz, there isn't, because assuming that there is such a thing is going to get you into these paradoxes where you have to give up Euclid's axiom that wholes are always greater than the proper parts, and he doesn't want to do that. And so the suggestion is that thinking about measure and thinking about Galileo's paradox and thinking about Euclid's axiom and whether to keep that or not is going to give us a grip on the distinction between Locke and Leibniz. And I would say that it also helps us get a grip on this distinction between like the actual infinite and the potential infinite that really keeps running through the history of the philosophy of the infinite right up till today. Right up till today. So I hope you enjoyed this look at 17th century authors with the help of Anat Schechtman in this article 3 Infinities in Early Modern Philosophy.